You know, we're surrounded by these incredible, sleek devices that just work. But have you ever stopped to think about the microscopic battlefield raging inside them? Today, we're going to pull back the curtain on this unseen war, the relentless fight against imperfection that makes your electronics actually do what they're supposed to.
I mean, really think about it for a second. That phone in your pocket, it's basically a tiny, sprawling city with information zipping around at insane speeds. So, what stops it all from just collapsing into chaos? Well, the secret is probably something you've seen 100 times, but maybe never really seen.
Okay, so it all boils down to the difference between a PCB and what's called a PCBA. A plain old PCB, that green board, that's just the empty city map, the blueprint. But a PCBA, that is the living, breathing metropolis. It's the board after all those tiny components have been mounted and soldered into place. And honestly, this assembled board, that's the real hero of our story today. Now, that jump from an empty map to a bustling city, it's definitely not an accident. It's more like a journey through this insane gauntlet of checks, scans, and some pretty brutal tests. So, let's do it. Let's follow one of these boards and see if it has what it takes to survive the process and actually earn a spot inside one of your gadgets.
So, our board's journey, it doesn't actually start on the factory floor. Nope. It begins way, way before that, back on a drawing board. You see, this whole war on imperfection, it's pretty much won or lost before a single component even gets touched. It all starts with the plan.
And that plan has a name, APQP, which stands for Advanced Product Quality Planning. The best way to think about it is like Minority Report, but for manufacturing defects. It's this whole structured process for thinking up every single possible way a product could fail, and then designing the solutions before you spend a dime on actually making the thing. It's all about preventing the fire in the first place, not just running around with a bucket of water after it starts.
And get this, the rules of the game are completely different depending on what you're making. There's this international standard called IPC that classifies all electronics. So for a class 1 product, like some cheap holiday lights, the main goal is just, does it turn on? But for a class 3 product, we're talking aerospace, medical devices, military tech, failure is just not an option. And this leads to some incredibly strict rules. For instance, a solder joint on a simple toy might only need to cover about 50% of a part, but on a life-critical device, it has to cover at least 75%. That tiny, tiny difference, it's literally everything.
All right, let's head down to the factory floor and see this thing get built. Now, the very first physical step, and you could argue it's the most critical one of all, it's not placing some fancy microchip. Nope, it's applying this gray, gooey stuff called solder paste. This paste is basically the glue and the electrical connection for every single component that's about to go on the board. And this is wild. Something like 60% of all soldering defects can be traced right back to this one single step. Think about that. If the solder paste is wrong, if there's too much, too little, or it's even slightly in the wrong spot, everything that comes after is compromised. It's the foundation of our entire little city, right? And if that foundation is shaky, the whole thing can just crumble. And that is why manufacturers are completely obsessed with inspection at this stage. A simple 2D camera can check if the paste is in the right place, but look here, it can't measure volume. It has no idea if there's enough paste to make a solid connection, or if there are subtle differences that could cause a total failure later on. That's where 3D inspection comes in. Modern assembly lines use it to build a full-on topographic map of the paste, measuring its exact height and volume. They can literally stop these defects before they even have a chance to exist. Okay, so once that paste is absolutely perfect, the real high-speed action kicks off. But watching over every single move is this silent, tireless army of robot inspectors. Their only job is to make sure every step sticks to that blueprint for perfection we talked about. So here's how it usually flows. First, you apply the paste. Then, a machine, that's the SPI we were just talking about, inspects it. Next, these incredibly fast machines start placing hundreds of components every single second. But, and this is key, before they get permanently soldered in this huge oven, another inspector, called an AOI, an automated optical inspector, double-checks their placement. Then, after the oven, the board faces one last barrage of checks, both optical and even X-ray. It's just checkpoint after checkpoint after checkpoint. These optical inspectors are looking for all kinds of trouble, but one of the most famous defects has a great name, the tombstone effect. This is what happens during soldering when, because of uneven heat or paste, one side of a tiny component actually lifts off the board. It ends up standing on its end, just like a tombstone. It's a total connection failure, and it gets caught in the act by the unblinking eye of a machine. But, some defects are way more sneaky. For these complex parts called BGAs, where you have hundreds of tiny solder balls hidden underneath, you can get a defect with another awesome name, head-on pillow. This is when the solder ball on the part and the solder paste on the board both melt, but they just don't merge into one solid joint. It ends up looking kind of like a head just resting on a pillow, which means you have a super weak or maybe even zero connection. And because it's hidden, it's totally invisible to a normal camera. That's why you need X-rays. And X-rays can spot even more dramatic failures. Ever heard of the popcorn effect? This is what happens when a tiny microscopic amount of moisture gets trapped inside a component. When that component goes through the intense heat of the soldering oven, that trapped water instantly turns to steam, expands like crazy, and cracks the component wide open from the inside. It literally pops, just like popcorn. And that's why components have something called a moisture sensitivity level and have to be stored in these super controlled environments. So, okay, our board has been assembled. It's been inspected. It looks absolutely perfect. But here's the thing, looking perfect isn't nearly enough. Now it has to prove it can actually survive the chaos of the real world. Welcome to the qualification tests, or as some people call it, the gauntlet. And this is just a little sample of the pure torture these boards are put through. I mean, they get subjected to extreme temperature swings over and over again. They get baked in ovens, blasted with moisture. They're hit with thermal shock, going from freezing to boiling in a matter of seconds. There are even machines designed to literally try and rip components right off the board. And the whole point of all this? To simulate years and years of abuse in just a few days. And sometimes the whole goal is to intentionally break the thing. It's called a damaging load test. Engineers will pick one parameter, say voltage or temperature or vibration, and they will just crank it up little by little until the board finally gives up and fails. The point isn't just to see if it breaks, but to find out exactly when it breaks and why. This is how you find the absolute, true limits of a design. So after this whole epic journey, from being just a digital blueprint to surviving actual physical torture, our little board is finally ready. And when you look at the whole process, you start to see the real unsung heroes of our digital world. Because that flawless performance that you and I just take for granted from our devices, it is no accident. It is the result of a calculated, relentless, and almost completely invisible war that's being fought against imperfection. It's 1,000 tiny battles won against chaos, against physics, and against simple human error long before that product ever gets into your hand. So, the next time you tap your phone screen or you power on your laptop, just take a second. Think about that invisible army of robot inspectors. Think about the brutal gauntlet of stress tests and all the meticulous planning that had to go perfectly right, just so that the tiny city inside your device could spark to life and not collapse.